Welcome back. So the last time we finished our review of linear algebra and we proceeded to talk about Rn. We wanted to start multilinear multivariable calculus. We agreed that it is important to study nonlinear functions, and we want to study functions from subsets of Rm to Rn, and sometimes when n is 1, these are called scalar fields. An example is the pressure, right? If you take the pressure of suppose you take a room and you look at the pressure at every point in space, right? So that is an example of a scalar field. It varies from point to point. When n is larger than 1, sometimes these are called vector valued functions or vector fields. What's an example of a vector field? Well, we'll see later on, but the physical example, if you will, is if a river is flowing, right? The velocity of at every point is a vector and it varies from point to point. There's an example of a vector field. Yeah. All right. So what do we want to do? We want to talk about calculus of this. That is, we want to define things like limits, continuity, differentiability, etc. On paper we would want to do integration also, but that's not a part of, that's beyond the scope of this set of lectures. So we will do multivariable differential calculus. Yeah. Okay, so that's what we want to do. We want to know how fast functions which are not linear change. Yeah. Right. So recall that for one variable you say that f from u from R to R is continuous at a point A if what happens? If for every epsilon greater than 0 there exists a delta which depends on epsilon which is greater than 0, such that whenever x is delta close to A and in U, then f of x is epsilon close to A, to f of A, right? Meaning you can make f of x as close to f of A as you want by making x close enough to A, right? So to even define this concept of continuity, to even define continuity for multivariable functions, of the type I mentioned, we need to be able to measure distances. In what sense? We need to know how far f of x is from f of A. Rather, you need to tell me how far f of x can be from f of A, the error tolerance if you will, and I'll tell you how close x needs to be to A, right? So you need to be able to measure distances, right? So how do you measure distances? We will usually use the usual dot product in Rn, defined in the usual manner, v1 w1 plus v2 w2, etc. And the norm coming from it, so the distance between v and w is defined to be the L2 norm coming from this, which is v1 minus w1 square, v2 minus w2 square, and so on. Yeah. Okay, now we can define the convergence of sequences. A sequence xn vector converges to x vector if what happens? Xn gets closer and closer to x as n gets larger and larger. In other words, if you tell me how close you want to be to x, I'll tell you how far into the sequence you need to go. There exists an n epsilon larger than or equal to 1 such that this is epsilon close to x if n is larger than n epsilon, right? Now you can very easily conclude that a sequence converges. This is said to be converging to x. Xn converges to x if and only if each component converges. That is, if you take xn's first entry, it must converge to x1. xn's second entry must converge to x2 and so on. And this happens if and only if this happens. So in other words, the convergence of a sequence of vectors in Rn is simply the convergence of a bunch of real numbers, n real numbers, right, as n sequences of real numbers rather. Yeah. Okay, so that's fine. So it's easy to find out when sequences in Rn converge. You simply look at each component and you just treat them as convergence of sequences of real numbers. Okay. So for one variable, the definition of continuity is easiest to visualize when U is an open interval. That is, it's easiest to talk about the continuity of a function when U is an open interval, right? Because that's where, so when you're on an open interval, it's really, and if you want to say that a function is continuous here, you say that nearby, you just look at the values of the function, they better get closer and closer to the value here, right? So the question is, what is the analog of an open interval in higher dimensions? We need to generalize open intervals to higher dimensions. There is no unique generalization. We can look at open balls or open rectangles. Yeah. An open ball, BAR, in Rn, centered at A with radius R positive, is basically the set of all x in Rm such that x is at most of a distance of R from A. Okay, that's an open ball. Okay, it looks like this. Yes. So that's an open ball. An open rectangle is supposed to look like this, right? So an open rectangle is simply a Cartesian product of a bunch of intervals, is an open rectangle. Yeah. So these are two ways to generalize open intervals to higher dimensions. Simply take the Cartesian product of an open interval or take an open ball. Both are useful things for us. Now the point is, right, so what is an open set? Open set in Rm, and in Rm. So first of all, what is an open set in R, right? Now whatever it is, the property it must satisfy is, it must be a set that allows us to do calculus, right? For example, if you want to talk about the derivative of a function, you'll take this, right? This is the derivative of a function, of a one variable function, right? So in other words, if x is in the set, x plus h must also be in the set for all small enough h, in quotes, right? That's an important property that it must have, right? In other words, a set U in R okay, this is a definition, is said to be open if around every point there is an interval. If whenever x is in U, x minus epsilon comma x plus epsilon is also in U for some epsilon that might depend on x actually. Okay. So, whenever x is in U, a small open interval around x is also in U, right. That is exactly what this means, right. So, likewise we can, motivated by this, we can make a definition in higher dimensions as well. Suppose S is a subset of Rm, okay, and A is inside S. Then definitions, A is called an interior point of S if there exists an R positive such that the open ball is contained completely in S. Meaning, suppose S is like this, okay, suppose this is S. An interior point is some point inside. So, in other words, there must be a small open ball around it contained entirely within S. In other words, just like in one variable calculus, to define the derivative, you need to be able to move a little bit away from x, and all those points must lie within your domain. Same thing here, okay. So, this is called an interior point of S, right, okay. A set U in Rm is said to be open if all points in U are interior points. So, in other words, an open set is supposed to look like this. So, it is said to be open if you take any point and if you take a small enough ball around that point that lies entirely within this set. So, here some examples and non-examples, if you will. So, 0 is not an interior point of this set, right. Why not? Because if you, no matter how small an open interval you choose around 0, the entire thing cannot be in 0, 1. There will be points which are slightly less than 0 in that open interval. So, they can't be in 0, 1. So, it is not an interior point. On the other hand, half is certainly an interior point of 0, 1. Why? Because if you take half, surely there is some smaller interval, let us say this is, let us say 1/3 and this is, let us say 3/4, which lies entirely within this, right. Likewise, in higher dimensions, for example, 1 by root 2 and 1 by root 2, or let us say minus 1 by root 2, 1 by root 2 is not an interior point of the set norm x is less than 1. Why not? This the norm of this vector, the L2 norm if you wish, is actually equal to 1. So, if you take a small open ball around it, you will certainly find, no matter how small an open ball, you will find points in that open ball whose norm is larger than 1. So, they cannot lie in this, okay. I mean, think about it, by the way, this is an exercise, you need to be able to do it rigorously, it is a very basic exercise. On the other hand, if you take 0 comma half, it is an interior point, okay, of this set. Norm of x comma y is less than or equal to 1. Okay, so think about that. This is also an exercise. No point is an interior point of this particular subset of R2, which is defined as a bunch of finitely many points, let's say. Okay. No point is an interior point, because obviously if you take any point and you take a small open ball around it, it will have infinitely many points in it, but there are only finitely many points in this set, right. Okay, some more terminology. Again, recall some more terminology here. For a, maybe I'll call this as a definition. For a general set S in Rm, the interior is the subset of all interior of S, sometimes written as int S, is a subset of all interior points. Okay. Right. Now, the interior could potentially be empty. In this case, there is no interior. Okay. It could potentially be a strict or proper subset, for example, in this case. It could be the entire set itself if the set is open, right. Okay. The second point is an open set containing a point A in Rm is called a neighbourhood of A. Some books call it an open neighbourhood of A, but we will just call it a neighbourhood of A. Okay. So, let us do a couple of more examples of open sets, or examples, non-examples of open sets. So, we will do some examples and then we will recall some other concepts from Rn, and then we will go to the actual subject material of this course, or at least the first half of it, which is multivariable differential calculus. Yeah. Okay, here is an example. So, an open ball is an open set in its own right, is an open set. What would this mean if you take any point? So, in other words, if I take an open ball x, this is A, I need to be able to find a smaller ball containing x which lies entirely within this, right. So, if x is in the ball, then of course x is at most at a distance of A from R. So, we need to find a smaller ball centered at x, that is the crucial point, that also lies within the ball. Well, you can choose any ball such that this ball does not hit the boundary of this ball, right, it shouldn't hit this. So, in other words, if for example, you consider all y in Rn such that the distance from x is not too large. Okay, how large can it be? Well, if this is x minus A, if this distance, and if this distance is r, it can be at most this much, right. So, why don't, for good measure, we will take this and divide by 2, right. So, if that is the case, then all such y do belong to this open ball. Indeed, if you look at the distance of y from A, this is, you add and subtract an x, and then you use the triangle inequality. Right. So, and using this, you can prove what you want. Indeed, this is less than r minus x minus a divided by 2 plus x minus a, which is r plus x minus a divided by 2. But x minus a is at most r, so this is r. Okay. So this is just making this geometric picture rigorous. So every open ball is an open set. Why? Because if you take any point within an open ball, you have a smaller open ball centered at that point. That's a crucial point, which lies entirely within the set. So geometrically it's obvious, but the way you prove such things rigorously is you take the geometric picture and you literally make it rigorous, right? I mean, what must be the radius of such a small open ball? It must be at most r minus norm of x minus a. So might as well take a underestimate such a radius, divided by 2 for good measure. The only thing is to use the triangle inequality. That's the only tool we have at our disposal, and you'll be done, right? I did it in detail this time because you need to get used to these sorts of arguments. What about an open rectangle, right? So suppose I take 0 1 cross 0 2, that is x lies between 0 and 1 and y is between 0 and 2 is open. So if we draw a picture, it will look like this. Again, how do you prove that? You take a point here, let's say take a point a comma b, we need to come up with a small open ball around this point that lies entirely within this rectangle. So suppose a comma b is inside this rectangle. In other words, a is between 0 and 1, b is between 0 and 2, right? Then we need to come up with a small ball around AB which lies entirely within this rectangle. How large can the radius of that ball be? Well, what is this? I mean, so sorry, the picture was probably a bit misleading. Maybe I should have drawn it like this. The vertical direction is larger than the horizontal one. Nonetheless, the point is the radius of the ball, so what is this distance, right? This distance is what? It's 1 minus a. This distance, sorry, this distance is a, this distance is 1 minus a, likewise this is b and this is 2 minus b. Certainly the radius of the ball must be less than these numbers. So if we take this ball, this is less than half of whatever it can be less than, the minimum of these numbers, right? If I take this, this is a ball of with center AB and radius r positive, where r equals this. The claim is this ball lies entirely within the rectangle. What would it entail to prove such a claim? We would need to prove that x is between 0 and 1 and y is between 0 and 2, right? If it's so need to prove that this implies x is between 0 and 1 and y is between 0 and 2. Okay, why is this so? This is the thing we need to prove. Now again, how far is x from a? So x is, so please note that this thing here is what? It's x square plus y minus b square. In particular, it's certainly larger than x minus a. It's also larger than y minus b, right? So in other words, x minus a mod is less than this, y minus b is certainly less than this. So x minus a is certainly less than the minimum of a comma 1 minus a by 2, because if you add more things, this minimum will only reduce. Likewise, y minus b is certainly less than this, right? So this means x is indeed larger than 0, less than 1, and likewise for y. And why is that so? Okay, why does this imply this? Well, again, it's by the triangle inequality, and I urge you to do this on your own. Okay, why do these things imply what I just said? Okay, right. And this is a more general phenomenon. This will also be an exercise, version of it will be in the homework. If U is open, and V in Rm is open, then the Cartesian product U cross V in Rn cross Rm is open. Okay. This is not trivial, it requires proof. So here is a non-example. If you take 0 1 cross 0 2, it is not open. Why? Because 0 is not an interior point, that is 0 comma 0 is not an interior point. For an open set, every point must be an interior point. Why is 0 comma 0 not an interior point? Again, I urge you to think about this rigorously, but the basic idea is if you take 0 comma 0 and you take a small open ball around it, it will certainly contain points where the x coordinate is slightly negative, which means it cannot lie, the x coordinate must lie in this interval, but that won't happen. Okay. Okay, please think about this. Right. Now, if you take the set 0 1 cross 0 2, this is open, but if you take the union with this particular point, this is not open. Why not? Because if you take this point, it cannot be an interior point. If you take a small enough ball around this point, it will contain points which are not here, right? So in other words, no small enough ball around this point can ever be a subset of this. So this is not an open set. Okay. This is an example of what's known as an isolated point. Okay. So an isolated point, the picture would look like this. It's literally isolated, right? So maybe I'll do a couple of more definitions. Right. Okay. Definitions. A point A in Rn is said to be the opposite of interior is exterior if what happens? So what would the something like an exterior point be? If this is S, exterior should lie somewhere here, right? What would that mean? If you perturb it a little bit, it should still be exterior, right, morally speaking. So that means it's interior to the complement. If A is in the complement of S and is an interior point of the complement. What that means is simply if A lies outside S and a small ball around A also lies outside S, yeah. Okay. So for example, if you take this ball centered at the origin with radius 1, okay, this open ball. Now if you take the point say 1 comma 2, okay, this is an exterior point. Why is this an exterior point? Obviously this point lies outside this open ball, its distance from the origin is larger than 1. Now if I take a set of all a small enough ball, the distance of all the points within the ball will also be larger than 1. How small a ball must I take? Again, I'll leave that to you as an exercise. Okay. So this is an exterior point. Yeah. All right. Now there are points, this is one definition. A point A in Rn that is neither interior nor exterior to S is called a boundary point. All right. So what is a boundary point? It's neither interior, which means if I take any small ball, it's not entirely contained within S, right? So it contains at least one point outside of S. And if I take any small ball, it's not entirely contained within the complement either. So there is at least one point from within S. So genuinely it's a boundary point. If I take any small enough ball around this, if I take any ball around this point, it contains points from both within S and from outside of S, right. So for example, 0 is a boundary point. Why is it a boundary point? If I take any open interval around 0, it contains points where x is less than 0. So in other words, points from the exterior of S, and points where x is larger than 0, those are points in the interior of S. I mean, in other words, the point, it contains, if I take any open interval, it contains points which are within S and within X complement. The fact that they are interior or exterior don't matter. There are points from within S and within S complement. So this open interval, no matter how small an open interval you choose, it's not completely contained within S or within its complement, right. So those are boundary points. Okay, the set of all boundary points is called the boundary of S, and it's denoted as with this weird symbol. Okay, right. Thank you for joining. We are out of time, so we'll continue the next time.